Okay.
Perfect. I see it's recording. Okay, perfect. Well, welcome everybody. It's my honor and pleasure, right, to introduce my student Luz Martinez-Lucas. So back in May 2018, yes, almost like 8 years ago, right? Luz took a linear algebra class in my that I have the privilege to teach, right? And I was very impressed with her performance, right? I recruit her, start working as an undergrad, received several awards as an undergrad, the Johnson's Research for Undergrad Experience. She received at least two of them, right? And then I asked her, right, whether she would like to do her PhD. So she said yes, and she has been working in my lab since all along till now. So her work was on emotional recognitions, and so I asked her to present for 55 minutes, right? And then we'll have questions. So I will, if there is some clarification question, please don't hesitate to interrupt. Otherwise, we can keep the question to the end to make this presentation more effective. So, Luz, the floor is yours.
Hi, everybody. My name is Luz Martinez-Lucas, and today I will be defending my PhD dissertation titled Context, Bias, and Dynamics in Speech Emotion Recognition. And my PhD advisor is Dr. Carlos Busso. First, I want to introduce the general field my work is in, which is affective computing. And affective computing aims to understand and model human emotions and emotional perception. To do this and to do many of the tasks in affective computing, we need emotional labels of data for for tasks such as analysis, automatic recognition, and synthesis of emotions. Since emotions are subjective, the most common method of obtaining these labels is conducting human annotations. On the right is an example of a person annotating some audio sample with an emotional category. Two major considerations of human annotations are the choice of method and the unconscious biases from human evaluators. My work focuses on automatic emotion recognition, and this aims to model and mirror the emotional perception capabilities of humans. Automatic emotion recognition is necessary for effective human-computer interactions so that a computer can formulate responses according to the emotions of the user. A modality that is common in emotion recognition is speech. And there are several applications of speech emotion recognition in fields such as customer service, where customers' emotional state could be tracked over a call to aid in workers in responding effectively, in entertainment, where knowing the emotion of a user can lead to more engaging interactions, in healthcare, where speech emotion recognition technology can aid in mental health screenings or in mental health check-ins that often occur over the phone. These applications would require a speech emotion recognition system which needs emotional annotations of speech and a good formulation of the speech emotion recognition problem. I look at both aspects in my work. A very common method for obtaining emotional annotations of speech is using a sequential annotation process where people listen to a speech segment, rate it, and then listen to the next and rate it, and so on. This process can lead to relative comparisons when people are going from one sample to another. A specific effect that can occur is affective priming, where a person can be primed with a specific emotion, which then can bias their annotations. And I will speak in more detail on this affective priming effect later in this presentation. A common annotation method, as I talked about, is sequentially annotating speech samples, and often these ratings are annotated in an isolated manner and treated as isolated annotations, which we call sentence-level annotations. However, emotional perception is dynamic and context-dependent. Therefore, annotations can be affected by the surrounding speech during evaluation, and sentence-level annotations do not allow for appropriate temporal modeling. Therefore, we can annotate speech with time-continuous annotations, which give the instantaneous emotional perception of an annotator at every frame of the audio, creating an emotional trace. These annotations give context to annotators and are appropriate for temporal modeling. This leads to an interesting question. How do these sentence level and time continuous annotations differ in the emotional space? I next look at the challenges in the formulation of speech emotion recognition problems. A common formulation is where we take a speech segment or sentence as input and output a single emotional value for the segment or sentence. However, natural emotions occur within contextual interactions, and nuanced emotions are dynamic throughout time. So both aspects are lost when we formulate this SCR problem as having an isolated segment as input and a single value as an output. So we can formulate the problem as a time series problem, which we call dynamic speech emotion recognition. So DSER takes as input a longer speech segment and then outputs an emotional trace. And my most recent work focuses on the developments of this type of formulation. Here is my presentation outline. I have just gone over my introduction where I mentioned the motivations for my thesis. I will next talk about my first 3 works where I focused on analyzing emotional annotations for speech emotion recognition. Here I will go over the effective priming effect on typical emotional annotations, the development of the MSP conversation corpus, and comparisons between typical sentence level annotations and time continuous annotations of emotional speech. Next, I will talk about my implementations of dynamic speech emotion recognition. I first explain the DSER baseline models I use for the MSP conversation corpus. Then I'll go over my proposed context encoder based on multi-hit attention developed for DSER. First, I'll explain my analysis of the effective priming effect on typical emotional annotations for speech emotion recognition. As mentioned previously, in the field of emotion recognition, a common way of obtaining emotional annotations is asking annotators to rate sentences out of context in random order. However, when people are asked to give a specific rating, they can often anchor those ratings on previously defined ones, which adds random context introduced by the annotation process. This anchoring could cause an effective priming effect, which refers to a phenomenon where an emotional event changes how a subsequent event is perceived. If you have an image with a clear emotion, it can change how a subsequent ambiguous image is perceived. So here the image on the right shows a clearly happy face. And if we look at this face first, then look at an ambiguous target face, we might notice maybe the crinkles beside the eye that might imply that this ambiguous face is happy. However, if we prime ourselves with more of a very clearly neutral face, the ambiguous target might seem a bit more neutral because we notice the flatness of the mouth. However, if we then look at a very clearly confused face, we might notice the crinkling between the eyebrows and we might see this ambiguous target as more confused. So this changing of our emotional perception in this example is the effective priming effect. So we ask, can this occur in our emotional annotations? In this work, we answer 3 questions. Does the effective priming effect occur in emotional labeling of speech? For example, if a rater annotates negative speech, will they rate the next sentence as more negative than it had seen positive speech? We expect to see an effective priming effect where the previous annotations push the current annotation closer to those previous values. Our second question asks if the effective priming effect is observed in both emotional attributes and categorical labels. And our final question is, if such an effect does exist, does it affect speech emotion recognition models? To answer these questions, we need to analyze annotation sessions with different priming sentences for the same target. Previous work in effective priming has focused on looking at written words, pictures, and faces. They have focused on the emotional attribute of valence, which measures the emotionality of an event from negative affect to positive affect. In these previous works, the perception of a target is usually pushed to the valence of the prime object. For example, if a participant is shown a positive prime image, such as a smiling child, their perception of a target image, such as a landscape, will be more positive. We can see this in the plot from previous work on the right, where we see that negative primes push the emotional score of a target more negative and positive primes more positive. It also shows that if a participant gets more experience time with the prime, the effect is more pronounced. In our work, we focus on effective priming in the speech domain and its effect on speech emotion recognition. We use 2 datasets for our analysis. The first is the MSP podcast corpus, which is a dataset of audio sentences sourced from publicly available sources. And the sentences are short, 2.5 to 11 seconds long, and are chosen using a speech emotion recognition model's expectation of emotional speech. So the segments chosen are not necessarily consecutive. After more processing of the audio, the sentences chosen are annotated in sessions of multiple sentences in random order. The corpus has ratings for the 3 emotional attributes of valence, which measures negative to positive affect, arousal, which measures calm to active affect, and dominance, which measures weak to strong affect, on a scale from 1 to 7. It also contains categorical labels of the primary emotion seen in each sentence. Each sentence has many annotations, all done by a different annotator in a different session. And for this analysis, we use version 1.11, which encompasses more than 230 hours of audio data. It has over 890,000 annotations annotated in over more than 71,000 sessions. The second data set we use is the big podcast corpus. And this data set mirrors the data collection and annotation of the MSP podcast corpus. However, the audio data of this corpus is in Taiwanese Mandarin as opposed to English. It also has ratings for the 3 emotional attributes and categorical labels of the primary emotion. And here we use version 1.0, which encompasses more than 96 hours of data. It has over 147,000 annotations, annotated in over 898 sessions. To measure if we have an effective priming effect for attribute labels, we need to first define and categorize a prime window for each annotation. To do this, we first separate all annotations into the sessions they were completed in. In this figure, we look at a session done by annotator 144 and their valence ratings. They first annotate sentence A, where they give it a valence rating of 3. Then they annotate sentence B and give it a rating. The annotator does these evaluations until they choose to stop. And all these annotations are considered one session. In this example, we want to measure the effective priming bias of sentence G by first defining its prime window. We do this by choosing all annotations started within 2 minutes of the annotation we are looking at of sentence G. Then we categorize this prime window depending on the values of the annotations within it. We consider a low prime window if all the values are 1 or 2, which means that the window shows calm priming for arousal, negative priming for valence, or weak priming for dominance. If all the values are between 3 and 5, then we consider it a neutral prime window. And if all the values are 6 or 7, we say it is a high prime window, which means it shows active priming for arousal, positive priming for valence, and strong priming for dominance. We note that most prime windows will not fit in any of these categories because we only see the ones that have these specific values, but our data sets have enough examples for our analysis. In our example, all the valence ratings in the prime window are 1 or 2, so it is a low or negative prime window. To then quantitatively measure the effective priming bias, we look at all the ratings of our target sentence completed by different annotators. Then we can compare the rating we are looking at, which we call the target rating, with an expected rating, which we define as the average rating of the other annotators for that sentence. We subtract the expected rating from the target rating to get a measure of the bias of a rating. In this example, a low prime window resulted in a negative bias. To see if we have an effective priming effect, we average the differences within each priming group. For all 3 attributes and both datasets, we see that high priming leads to a positive bias, low priming leads to a negative bias, and neutral priming to a near zero bias. We conclude that there is indeed an effective priming effect caused by previous ratings in our annotation process. This first analysis answers our first question. The effective priming effect occurs in our emotional annotations across languages. We also conduct analyses on categorical labels and see the same effect. You can see this analysis in my dissertation. If annotators annotate previous sentences with one category, the next sentence is more likely to be annotated as that category. This effect is consistent with previous effective priming studies of valence, where previous extreme emotional events push perceptions to that same extreme. Since we see the effective priming effect in emotional annotations of speech, we want to ask if the effect can impact speech emotion recognition performance. To do this, we need to quantify the bias resulting from the effective priming and use the labels that are biased by effective priming for speech emotion recognition. So we create an expected bias measure that is based on previous annotations done while rating a sentence. We can use this bias measure later to create bias groups of sentences. So we first define priming patterns as the attribute values of the 3 or fewer previous annotations during the rating of a sentence. Then we give each pattern an expected bias. So in this example, we have a session by rater 144, and we can give each rating of each sentence a different priming pattern. So if we first look at sentence A, we see that it's at the beginning of the session, so there's the priming pattern is no values. If we look at sentence B, the priming pattern is a single value of 3. If we look at sentence C, the priming header here is 3 and 5, so that is a priming pattern of just 2 values. And when we look at D, we have 3 previous values, so the priming pattern is 3, 5, 2. And if we look at sentence G, we only look at the 3 or fewer previous annotations, so the 3 previous annotations of 1, 1, 2. So each annotation of a sentence in a session will have a priming pattern and an expected bias. So how do we get the expected bias for each priming pattern? We decided to average the attribute differences as done in our first experiment. Instead of grouping by general priming type, we now group by priming pattern. So the average of each group is then the expected bias for each priming pattern. Next, we aggregate the annotation biases to create an effective priming bias for each sentence in our corpus. We do this by first getting the expected bias for each annotator of a sentence. This is done by looking at the session each rater rated that sentence. So in this example, we are looking at sentence G. We first note that rater 144 saw a priming pattern of 112 when rating sentence G, and the expected bias for this pattern is negative 0.749. We do a similar process for the rest of the annotators. Rater 1034 has no priming pattern since they rated sentence G at the beginning of the session. Rater 456 only saw 2 previous sentences. Rater 1321 only saw 1, and Rater 334 saw a priming pattern of 177. Then we average the expected bias of the annotators for the sentence. So the rest of our analysis focuses on the larger MSP podcast corpus as it provides more examples of each priming pattern. So after calculating the effective priming bias of each sentence in the corpus, we can build a histogram of the number of sentences with a specific priming bias value. We see this histogram for the arousal priming biases on the right. We ultimately want to explore how the effective priming bias affects speech and motion recognition models. So we create subsets of the corpus with different biases. So for each emotional attribute, the biases are centered around 0, so we define the negative subset as sentences with the lowest 20% of biases, the positive subset the highest 20%, and the first neutral subset the middle 20%, and our second neutral subset has sentences with biases between negative 0.02 and 0.02. We create these subsets for the arousal, valence, and dominance priming biases. Furthermore, each of these subsets has a different emotional distribution, which can affect the performance of an SER model. Therefore, we sample each subset to match the distribution of the full MSP podcast train set. We use the transformer-based model as our speech and motion recognition model. So we first use a Wave2Vec2 pre-trained model as an encoder. Then we add a downstream head consisting of 2 fully connected layers. And finally, we add a 1 linear layer with 3 output nodes for the attribute predictions. We fine-tune the Wave2Vec2 encoder while training the downstream head to predict our emotional values. And for our experiments, we train with the prime subset, so these are negative, positive, and 2 neutral subsets, and test with the full MSP podcast test set to see what the difference is when training with the different types of bias labels. Here we have the attribute results. And we train and test the model 10 times for each attribute. We use the concordance correlation coefficient, or the CCC, as our testing metric. And the CCC considers the absolute value differences and the correlation between 2 random variables. We report the average and standard deviation of the CCC between the predictions and the labels. We see that the models trained with the more biased subsets perform the best and have somewhat lower standard deviations. The models trained with the unbiased subsets perform the worst, with higher standard deviation in performance. Fortunately, the models trained with the subsets sampled from the full MSP podcast dataset, which means they have more unbiased sentences but still have some biased ones, perform slightly below the biased model. This is encouraging since that means our typical data does not lead to much worse models, and if we include all the data, we can have even better results. Overall, we see that the effective priming effect helps speech emotion recognition models, and that the standard deviation of the CCC results showed that the models could also be more certain. Next, I will talk about the collection and annotation of the MSP conversation corpus, a dataset of emotional conversations annotated for emotion using a time-continuous method. Our laboratory at UTD has previously collected the MSP podcast corpus. A limitation of this corpus is that it does not allow for the study of temporal and contextual information on emotions. The segments chosen are not necessarily consecutive, and they focus on one speaker, not providing any context. The segments are also annotated in random order, which does not give contextual information to evaluators, and therefore that information is absent from the annotations. Therefore, we decided to collect a database of time-continuous annotations as a complement to the MSP podcast corpus. We introduced the MSP conversation corpus, a corpus of naturalistic recordings of conversations sourced from larger podcasts. We focus on collecting audio with a variety of speakers and multi-party interactions, and we also focus on collecting conversations with a variety of topics and structures, and enough data to train modern models. We annotate our data with emotional attributes in a time-continuous manner to reflect the complexity and temporal dependence of emotions. The table on the right shows some of the most relevant databases with time-continuous emotional annotations. This main database approach creates its recordings by having an operator that expresses predetermined emotions, which are meant to elicit some emotional behaviors from a user. And this limits the naturalness of the emotions present in the speech. In the Ricola database, participants are shown neutral, positive, or negative stimuli before being recording solving a problem with another participant. And similarly, in the SEWA database, participants are also induced with emotional media before having recorded conversations. These databases have some intervention from researchers, which can not only detract from how natural the recordings are, but is also a more costly and time-consuming approach than used in our proposed corpus. In the MSP conversation corpus, speech data is gathered from already existing recordings found online. Two databases that use similar data collection as our corpus are AFWILE2 and MuseCar. AFWILE2 sources its data from online videos, typically single-person recordings, and MuseCar contains recordings of car reviewers in the wild, or some mostly single-person recordings. The MSP conversation corpus has recordings over a wide range of topics, with a focus on many types of interactions, making it suitable for a variety of applications. For our proposed corpus, we select 10 to 20-minute segments from the podcasts in the MSP podcast corpus. We call these conversations. These segments are chosen for their natural emotional content and their speakers. Since our podcasts come from the MSP podcast corpus, we have some idea of the emotions and speakers present in certain parts. So we can use that information when selecting our conversations. We want a broad range and a balance of emotions, as well as a balance of gender. We also look for diversity of speakers in the conversations. Our final release, Release 2.0, contains 310 conversations, which span 77 hours and 27 minutes. Next, I will explain the annotation process. All conversations are split into 3 to 7 minute segments to avoid fatigue while annotating. These segments are then loaded into the Karma software. The annotators use a joystick to place a cursor in a range from -100 to 100 at the level of their instantaneous emotional judgment of the intensity of the attribute they are annotating. They create an emotional trace for the audio they are listening to. So once each annotator has finished their evaluation, the annotations can be averaged per frame, which gives us our final annotations. Our final release contains annotations for 26 student workers from UT Dallas, and we have at least 6 annotations for each conversation segment and each attribute. To evaluate the reliability of our time-continuous emotional annotations, we calculate inter-evaluator agreements. We use Cronbach's alpha, which measures internal consistency between 0 and 1, and we measure the consistency between the annotators. This measure will tell us if annotators agree on trends, not if they agree on absolute values. The table on the right shows our inter-evaluator agreements. The last row shows the statistics for the full corpus. They show alpha values above 0.7 for all three attributes, showing acceptable consistency for arousal and dominance and good consistency for valence. We also perform speaker diarizations on the ELAN software. We manually annotate the start and end times of any speech or emotional sound a speaker makes, and the annotations are separated by speaker in the ELAN software for easy identification. So the pie chart here shows our conversations categorized by the number of speakers identified. This shows that most of the dataset is interactions between two speakers. However, a large part of the audio contains interactions between more than two speakers. The table on the right shows the breakdown of the apparent gender of the speech in our data. Not all speakers have a gender annotation, which we denote as unknown gender, and the last row shows that our dataset is well balanced between genders. With the collection of the MSP conversation corpus as a complement to the MSP podcast corpus, we can compare the two types of annotations these datasets use. Next, we will look at some of the differences between sentence level and time continuous annotations. In the previous analysis, we had looked at sentence level annotations, which usually contain a single score that describes the global emotion of a short segment. These annotations lack context during annotation and have low temporal resolution. Therefore, we also have time continuous annotations, which give frame-by-frame scores of instantaneous emotional perception. They provide context during the annotation process and have a high temporal resolution. Because of this, these annotations can be aggregated into sentence-level labels, allowing researchers to use them as sentence-level labels. Sentence-level labels are convenient for a lot of common emotion recognition formulation, which makes the aggregation of time-continuous annotations common for use in these formulations, leading to two questions. How do these aggregated and original sentence labels differ? And are aggregated time-continuous labels valid for speech emotion recognition problems? To answer these questions, we need overlapping datasets, where one has time-continuous annotation and the other's sentence-level annotations. Here we use the MSP podcast and MSP conversation corpora. We use release 1.9 of the podcast corpus and release 1.0 of the conversation corpus. We have around 2,884 overlapping sentences, which is more than 4 hours of speech data that we use for our analysis. The closest previous work to our analysis used the Creative IT database, which is a multimodal database of theatrical performances. The dataset contains time-continuous annotations for the three emotional attributes of arousal, valence, and dominance, as well as global annotations of the full performance. Like our work, the researchers aggregate time-continuous labels, but they aggregate those labels over the full performance, which they then compare to the global annotations. They utilize 6 aggregation functions, as shown in the table on the right, and they see that the labels are the most similar when the first and third quartiles are used. Our work is different in that we use these natural recordings and aggregate our time-continuous annotations over single sentences, which is much lower temporal resolution and are more common in typical SCR methods. In this analysis, we do utilize the aggregation functions used in this previous work. Here I describe our method of aggregating the MSP conversation time-continuous annotations into sentence-level labels that coincide with the MSP podcast annotations. We first collect the timing information of each overlapping sentence from the MSP podcast corpus. We use that timing information to split the individual time-continuous annotations of the MSP conversation corpus and aggregate them over the sentence timing. We get left with a sentence label from each annotator, which we then average over the annotators to get the final sentence level label. An aspect of time-continuous annotations I have not mentioned is that because annotators are instantaneously reacting to the audio they are listening to, their emotional traces will have some reaction lag. To take this reaction lag into account, we utilize 6 different constant reaction lags. To use them, we first shift the time-continuous annotations by the reaction lag, then perform the rest of the aggregations as before. To qualitatively analyze the difference between the labels, we take the Pearson correlation coefficient between the original and aggregated sentence level labels. Each box in the box plot here shows an aggregation method, and the boxes show the statistics over the reaction lags. We see that the arousal labels have the highest correlation and the dominance labels the lowest. We also see that aggregation methods focused on middle values like mean and median show higher correlation, which is encouraging since these are typically used when time-continuous annotations are aggregated in other works. Overall, we see that original and aggregated sentence level labels are indeed correlated. However, the absolute values are different even when accounting for scale differences. So these results show that although aggregated sentence level labels can approximate original sentence level labels, they are not interchangeable. To compare the usage of the two types of labels in speech and motion recognition, we first described our SCR method. Since we have a limited amount of data, we use a relatively simple neural network model. Our model consists of a feature extractor that extracts 6,373 high-level descriptors from each sentence, two fully connected layers, and a linear layer that outputs a single value. We build a separate model for each attribute and train to maximize the CCC. And we use the predefined partitions in the MSP podcast corpus for our models. We first train and test the models with all the types of aggregated sentence level labels 10 times, and we choose the best performing models from the aggregation functions and reaction lags. Then we train and test the models with the original sentence level labels 10 times. We report the average and standard deviation of the CCC between the predictions and the test labels. These results show that our original sentence level labels give higher performance for arousal and dominance, while the aggregated sentence level labels perform best for valence. Since we tested all the models in matched conditions, where the train and test labels come from the same corpus, we also trained them in mismatched conditions, where the train and test labels come from different sources. We observed that the arousal mismatch results are close to the match results, suggesting that the two types of labels are similar for speech and motion recognition modeling. The valence and dominance results show the opposite. The matched and mismatched results are different, suggesting that the two types of labels show significant differences for SER. We also perform statistical significant tests on the model results between matched and mismatched conditions. Highlighted are the results that show significantly higher performance over their matched or mismatched counterparts. None of the results for the arousal model show statistical significance. For valence, the models trained with the aggregated labels perform significantly better than the models trained with the original labels, regardless of the test set. And for dominance, the models trained with original labels show significantly better performance than the models trained with aggregated labels when testing on those original labels. And it performed better, but not significantly better when testing on the aggregated labels. So the use case for each type of label depends on the speech and motion recognition task at hand, and the usage of the two types of labels together must be done carefully. With the collection of the MSP conversation corpus, we can train a model to predict emotional traces as opposed to just predicting a single value for an emotional sentence. After the development of the MSP conversation corpus, we built these dynamic speech motion recognition models to obtain baseline results when using the corpus. So, as I previously mentioned, typical speech emotion recognition often predicts one emotional value for a short speaking turn, which ignores that natural and nuanced emotions are dynamic throughout time. Another formulation is dynamic speech emotion recognition. Here, the problem is formulated as a time series problem. Sequence-to-sequence modeling is often used in these time series problems. A type of sequence-to-sequence method that has been used for DSER is a recurrent neural network. These models keep intermediate states throughout time to save information that could be relevant for future time step predictions. And RNNs have been used in previous work for multimodal dynamic emotion recognition and also noisy DSER. A downside of these models is that they are sequential in nature and therefore can forget information as time goes on, and they cannot use information from the full time series to predict each time step. And as well, that their recurrence limits their use in real-world applications. Another type of model that is used in DSER are convolutional neural networks. Previous work has shown that they outperform an RNN model, and they are currently popular in DSER methods that compensate for reaction lags and time continuous annotations. So these CNN models encode temporal context by using a small contextual window surrounding the current time step. And this context window might lose general or long distance context useful for emotion recognition. A more recent sequence-to-sequence model is a transformer, which does use the full time series to predict each time step. Its multi-head attention layers can see all the time steps and their relative position when positional embeddings are added. However, these types of models are very large, so for longer time series like in this work, they either must use smaller contextual windows or become computationally intractable. This limits how much the time series they can use to predict each time step. We want to provide baseline results with our MSP conversation dataset. So we build a dynamic speech emotion recognition model by first using a WaveLM self-supervised learning network to extract speech representations. We use the WaveLM large pre-trained architecture. The WaveLM network is transformer-based, and it is trained using short speech segments, so the contextual window is limited. We further use a WaveLM encoder that has been fine-tuned using the MSP podcast dataset for the task of segment-level speech emotion recognition. And we freeze the WaveLM network, and to predict our emotional traces, we train some linear feed-forward layers plus an SCR head using the CCC loss. We use 3 different SCR heads for our baseline models. The first is a simple 4-linear neural network. The second is a 2-layer bidirectional LSTM model, which is an RNN-based model. And the final follows the transformer decoder structure. We train our models under 2 task options, single task for predicting 1 attribute at a time, and multitask for all attributes at the same time. We train and test our models 5 times and report the average CCC over test 1 of the MSP conversation corpus. Overall, we see strong baseline results, especially for the 2-layer BiLSTM SCR head. In my most current work, I proposed a context encoder based on multi-head attention to enhance dynamic speech emotion recognition. As mentioned in much of my previous works, emotional perception is context-dependent. Typical DSCR models only use temporal context using the representation information from surrounding time steps to predict the current one. However, the complexity and subjectivity of emotions encourages the use of additional context through a context encoder. This additional information can include the mood of a conversation, speaker emotional baselines, or other useful information. These types of context can be provided by observations. We define observations as emotional estimates of a few time steps of a conversation. Accurate or perfect observations can be obtained from people in human-in-the-loop system. And these settings can be seen in the real world where human experts are available but in limited supply. They can be asked to evaluate a small number of speech segments, and the automatic system can evaluate a much longer interaction. We can also get these observation estimates from speech emotion recognition predictions, where we can try to choose predictions with high confidence for better results. Our previous work utilized a conditional neural process model. This type of model is a conditional stochastic process that conditions predictions on observations. And to properly explain this model, I will first talk about typical supervised learning. Typically, we have a set of feature label pairs that we use to train a model. Then we use the test features to condition the model to predict the corresponding outputs. In a conditional neural process, the model first uses a few feature label pairs of a time series to represent the full series, which are our observations, and the pairs are encoded using a model to extract information relevant to the full time series, and then these encodings are aggregated into a single encoding. The final encoding is used as a second prior to the model that predicts the outputs of each time step. So our previous work obtained impressive results when using perfect observations, meaning using the labels as our observations. And we also trained and tested the conditional neural process model using predicted observations, which limited the results. A limitation of our previous model that we aim to overcome in our current work is that it does not give fine-grained context. The conditional neural process model uses a single representation for the observations for all the time steps. In our current work, we aim to use a representation of the observations that is specific to each time step. When developing our model, we set out 3 general steps that it should do. First, the model should sample observations from the time steps, meaning that it should choose certain time steps, then get emotional estimates for those time steps. Second, our model should decide when an observation is relevant to each time step by both how far away in time the observation is and how similar the speech representations are. Finally, the model should use the relevant observations to predict the emotion at each time step. Here I show our full proposed model. In blue, we see the network that outputs the speech representations. We use the same model as our MSP conversation baselines. In orange, we see the network that outputs our observation embeddings. We use the same linear observation embedder as in our previous conditional neural process model. The embeddings are based on the emotional estimates and speech representations of the observations. In green, we see our proposed block, the context encoder. We use a multi-head attention layer to obtain speech representations with added context from the observations. And in purple, we see the final speech emotion recognition head. We used a simple 4-layer linear network used in our MSP conversation baselines. We add an additional connection from the context encoder multi-head attention output to the second linear layer to increase the influence of the observation emotional estimates. So next, I will explain our context encoder in more depth. We base our context encoder on work by Chang et al. They use a speaker context encoder based on multi-head attention to enhance automatic speech emotional recognition of specifically hard to understand words. We also use multi-head attention in our context encoder, but we use different vectors for our value and key inputs. As a brief reminder, multi-head attention uses scaled dot product attention. The dot product in dot product attention, the dot product of the query and key vectors is taken to produce a similarity score between each pair. Then those scores are converted to weights using softmax and are multiplied with the value vectors to get a weighted average of those vectors for each query vector. And multi-head attention then concatenates multiple heads of scaled dot product attention. For our context encoder, we define the query vectors as all the time step speech representations, the key vectors as the speech representations of only the observations, and the value vectors as the observation embeddings. The layer would compare each query vector, so each time step representation, with all key vectors, which are the time step representations of each observation. And then we will get a weight for each observation for each time step. The weight will be larger if the time step is more similar to the observation. The multi-head attention output will be a weighted average of the observation embeddings for each time step. And the full output of our context encoder will be speech representations of all the time steps with knowledge of the relevant observations at each time step. We further add positional encodings to the query and key inputs since they are more similar when closer in time, and we want the multi-head attention to take into account when the observations and each time step are close in time. We perform our experiments of the MSP conversation corpus under various settings. We use 2 types of observations. Labels are the perfect observations, representing a human in the loop setting, and prediction. And we also have predicted observations, and prediction of the observations come from a speech emotion recognition model trained on the MSP podcast corpus. We choose the time steps for the observations in 2 ways. We find success in using a random but uniform strategy so that the observations are equidistant in time. And when predicting the observations, we can also obtain an uncertainty measure that will hopefully tell us which predictions are more accurate. So we use Monte Carlo dropout to estimate the uncertainty of our speech emotion recognition model predictions. We first look at our valence results. And here we first compare our previous method of a conditional neural process model with our context encoder, where we see an increase in performance, CCC performance. We can also compare our base model, and this base model is our full model without the context encoder, and using our kind of end-to-end method where we are predicting our observations, and we also see an increase in performance for valence. However, when we try to choose accurate predicted observations by using uncertainty, we see that this lowers performance, and this could imply that using Monte Carlo dropout is not an effective method here for choosing accurate observations. We can then see our arousal results, where we see similar results in that our proposed method, our context encoder, performs better than our previous conditional neural process model. However, we see here that using our predicted observations decreases the results compared to our base model without a context encoder. They could imply that our predicted SCR speech emotion recognition observations are not accurate enough for using as extra context. And then when we compare, again, using random predicted observations with low uncertainty observations, we see that the uncertainty measure might not be appropriate for this problem. And finally, looking at our dominance results, we see similar results to valence, where we see an increase from our previous conditional neural process method, an increase on the base model compared to using predicted random observations, and again, an uncertainty measure that does not seem appropriate for this problem. To ascertain that our proposed context encoder does give more fine-grained context than our previous conditional neural process model, we compared their arousal predictions of the same conversation. We give the model observations, then the models predict the arousal trace. We see that our proposed context encoder leads to a prediction that follows the observations more accurately, and this shows that our proposed model is able to add fine-grained context to our predictions. In this last section, I will conclude my thesis work and provide a summary of my contributions. The first work I presented was on affective priming effect in emotional annotations of speech. My work showed that the affective priming effect does influence emotional annotations across languages and label types, and it was also able to show that the effect results in biases that measurably impact speech-emotion recognition modeling results. Overall, my work here highlights the importance of unconscious biases in human emotional annotations, especially biases that come from contextual information. My next work introduced the MSP conversation corpus, a dataset that I utilized in the rest of my works. This corpus established our large-scale naturalistic benchmark for dynamic speech emotion recognition. The dataset contains naturalistic speech from a variety of speakers and multi-party interactions, and these interactions involve a variety of conversational topics and structures. The speech data that was annotated with rich time-continuous annotations, and a unique aspect of this corpus is its overlap with the MSP podcast corpus. In my work, we were able to compare the two types of annotations in the datasets, giving important insights into the usage of both types of annotations. Finally, we were able to train dynamic speech emotion recognition models with our proposed corpus to give baseline results for comparisons in future work. I briefly touched on my work in modifying a conditional neural process model for dynamic speech emotion recognition. Here I provide a graphic of this model. My work here highlights the potential for conditional neural process models in these types of problems, where we can see competitive results. The neural process family of models are also very flexible. The networks that can be used in its structure are not fixed, and its method of aggregating observation embeddings makes real-time prediction easy to implement. Finally, I talked about my most current work in dynamic speech emotion recognition. I proposed a multi-head attention context encoder that can incorporate sparse but informative emotional estimates into a DSER model. Adding these estimates greatly improves performance, making this proposed framework ideal for real-world human-in-the-loop applications, especially those where human experts are available but in high demand. Here's an overview of the contributions of my dissertation. They are split into two sections. The first is on contextual information and dynamics in emotional annotations, where I analyzed the affective priming effect in our annotations of speech, proposed a measure of expected bias from the affective priming effect based on the annotation sequence done by an evaluator, detailed the development of a naturalistic emotional speech corpus annotated in a time-continuous manner, and provided a novel analysis of the aggregation of time-continuous emotional annotations into sentence-level labels. The second contribution section is on machine learning techniques for dynamic speech emotion recognition, where I provided DSER baselines using our large publicly available dataset, developed a conditional neural process model for DSER, and proposed a novel multi-head attention context encoder for DSER that can be used for human-in-the-loop applications. I would like to thank the National Science Foundation for supporting my work. Thank you very much for your time. Here's the summary of the core published and submitted works for my dissertation. And here's a list of other publications not used in my dissertation. Any questions?
I think if I may, I have.
Thank you. Thank you, Luz, for your presentation. I think we can go ahead.
I think now it's a next step where we have all questions from a general audience.
Yes, I have a question, if I may.
Sure, please.
Thank you. Luz, I should say that congratulations, you've done a great job. Recently, I started working on SER on a project, and I've read most of your works, and they were so inspiring. And now that I sat at your defense and I saw how you looked at SCR and emotion and how you changed, how you looked at emotion during the time and how subjective it is. I should say that this is so inspiring, and I'm so happy for you, and I wish all the best in your career. So I have a question as well for you as well. If you, based on all the experience you have and the emotion, if you wanted to have a model to do the SCR, not in a conversation, but you have only one utterance, one segment, how would you do that? How be, because this is so subjective, and I also looked at MSP podcast corpus and I saw that there's a lot of annotation disagreements between the different annotators. So I would like to know, how would you do that?
I think I understand what you're asking. It is a hard thing, especially when we're dealing with just single sentences and we don't have too much context. In that case, I think it is best to kind of try to decide. You as a model builder has to decide how like the model will predict a specific sentence, right? You cannot, I think it's hard to say that, oh, this is going to be the perfect emotion recognition that everybody's going to agree with. But if you are able to just get the model to decide on a specific type of emotion recognition. So as you said, if you have something, some human annotations that are not in agreement with each other, you might just choose a specific type of annotator. So a specific perception in that case, so that your model can predict something would be kind of the way I would start approaching it. Because we want our model to have human capabilities, and humans are not perfect either in emotional perception, whatever we can define as perfect.
Thank you. Great. But if you could just clarify this for me, I would appreciate it. If you wanted to do this, would you do this using the valence, arousal, dominance, or would you do it as a category?
I think that really depends on the application you're trying to use the model for. Like using a category can be good enough when you're just trying to kind of get a mood of what's happening. But if you want to be more specific, or especially if you want to look at very natural emotions in a conversation where there's not a lot of extremes, arousal, valence, and dominance might be more helpful there. But if you just want to know, oh, this person is happy at this moment, the categories might be sufficient there. Thank you. Any other questions?
There's no more questions from the audience, right? Maybe we can give Luz more applause, right? And then we will ask you, right, to leave the meeting. By the way, Luz, can you turn off the recordings?
Yes. Let me see.
Thank you, everybody, for coming. So
You get thunderous applause.
look at this.
Everyone is emotional.